Nice. So, hi everyone. Welcome once again to another Most Talk. This is the last of this first season. Today we have with us Richard Montgomery. So, Jelena will talk about his impressive CV.
So in 2007, Richard began his study at the University of Cambridge. He graduated in 2011. In the same year, he enrolled PhD studies at the University of Cambridge under the supervision of Andrew Thomason, and he obtained a Doctor of Science degree in 2015. From 2015 to 2019, he worked as Junior Research Fellow in the Trinity College, Cambridge. After that, he worked at University of Birmingham from 2018 to 2022. After that, he became associate professor at the University of Warwick. In 2024, he got a position as a reader at the University of Warwick. Area of his scientific interest is vast, and he is working in extremal and probabilistic combinatorics. Richard has published more than 30 papers in premier mathematical journals. He was awarded many times. In 2019, he received the European Prize in Combinatorics. In 2020, he obtained ERC starting grant, and in the same year, he received the Philip Leverhulme Prize. In 2024, Richard won a prestigious EMS prize at the European Congress of Mathematics for his work on pure maths of networks, also known as graph theory. So if you have any questions, you can ask Richard during his lecture or after the lecture. So Richard, you can start, and thank you.
Thank you. Thank you for the introduction, and thank you all for coming along and for the invitation to talk to you today. So today I'm going to talk to you about Latin squares via graph theory. I'll maybe try and keep an occasional eye on the chat if you do have any questions in there as well, but probably best is just to interrupt me. Okay, so I can't see it. Okay, so I'm going to talk to you a little bit about Latin squares and how you can study them via graph theory. So let me get started. Great. Okay, so I work in combinatorics, as Jelena said, and usually we study some combinatorial structure and something within that. So I thought to pin us to the area of combinatorics, what I'll be talking about is Latin squares, as I'll explain, and then I'll be looking within them for transversals. Okay, so I'll come back to obviously the definitions of that in a moment. Just to give you an outline today, I'll introduce these topics, and then I'll go back and give you a little bit of history of how the study of these came around. And then I do extremal and probabilistic combinatorics, so I'll talk about what we can say about Latin squares from these two different perspectives. So that's really saying, in extremal combinatorics, we're interested in what we can say about every Latin square. So what are the extremes? What's the sort of odd behavior that might occur? And in probabilistic combinatorics, usually we want to ignore that and just see what a typical Latin square might look like. Okay, so here's the definition of a Latin square. We take an n by n grid, and we're going to use n different symbols, maybe the numbers 1 up to n, and we put them into this n by n grid so that each symbol appears exactly once in each row and each column, like for example here. And this is something you might recognize. Indeed, this is the grid of a Sudoku puzzle from the New York Times that hopefully I got correct. If we delete the 9 by 9 subsquare conditions and so on, then the underlying 9 by 9 grid here is a Latin square of order 9, using the numbers from 1 up to 9. And within the Latin squares of order 9, I will be looking for a transversal, which is a set of n cells, here 9 cells, with which share no row, column, or symbol. So for example, here I've used the colors to highlight these are different symbols, and you can see there's one cell highlighted in each row and one in each column. Okay, so before I talk about transversals, maybe I'd mention a little more about Latin squares. So the sort of canonical example of this you have at your fingertips, aside maybe from Sudoku squares, depending on your recreations, are the Cayley tables of groups of order n. So here I have the Cayley table for the integers mod z. So the rows and the columns are identified with 0 up to 6, and within the cell I've put the sum of those two elements. And from the rules of group theory, this gives me a nice Latin square. And there are also really strong links from the study of Latin squares to design theory and combinatorial designs. Latin square is a particular sort of combinatorial design. And there are also links to error-correcting codes in two-dimensional permutations and finite projective planes. Okay, so I've introduced you a combinatorial object and some substructure between it. And I've highlighted a transversal. So there is a transversal in that Latin square in the leading diagonal. So the sort of main or first question you might have is, does every Latin square have a transversal? And here I put the answer. So when the order of the Latin square is even, there may be no transversal. And the canonical example here is in the group Z mod nz, when n is an even number. And more generally in abelian groups, if the sum of the group elements is not equal to the identity. So here is Z6, which I'm claiming has no transversal. So suppose I took 6 squares here. So this is Latin square of order 6. So I take 6 squares and ask, can this be a transversal? And you can see I've highlighted 1 from each row and from each column. So what I want is for those 6 cells to be the numbers from 0, 1, 2, 3, 4, 5. So can they be that? Okay, so to argue they can't, if we just add up the entries in those 6 squares, we know that the entry is the sum of its row plus its column. So really what's going on behind this is I'm adding up every row, and then I'm also adding up every column. So I'm getting twice the sum of the group elements every row, and then for the second go around every column. And therefore, this should be equal to 0. But the sum of the elements itself, so I say this is equal to 0 in this particular case. So the sum of the elements itself, if that were a transversal, they would also be equal to the sum, but in this case, this is equal to 3. Okay, and you can see that I tried to find a transversal here. I didn't manage it. The entry in the 4th column and last row there is 2, and I wanted it to be 5. So it's off by 3, the difference in these two sums. Okay. So in general, what we've shown here, you can do this more generally and show you can't have a transversal if the sum of the group elements isn't equal to the identity. And this is essentially, in the abelian case, it's not too difficult to show this is sufficient to show that there is a transversal in the Cayley table. And this was proved by Page in 1947. But more generally, in the non-abelian case, it's much more difficult. And this is subject to the Hall-Page conjecture. So don't worry too much about this condition. All this is some condition on a group that should say whether or not there's a transversal in its Cayley table. So this is a conjecture from 1955. And we do now know that it's true. So it was proved, but just repeating the conjecture there. So it was proved by 2009. They're very long proof if you take the total sum of all the work towards it. So it goes by the classification of finite simple groups. And one of these authors proved a reduction to the different cases you need to check, and then the other check those cases. So it was proved by 2009. I'll just mention in passing, so an interesting aspect of this is we have 2 different proofs now of this conjecture that just hold whenever the order of the group is very large. So we have a proof that works by analytic number theory, some version of the circle method, by Eberhard, Manners, and Mrazovich. And around the same time, there's also a very combinatorial proof for large groups by Pokrovsky and Liasim. Okay, so this gives us good answers we can hope to get for the Cayley tables of groups. But more generally, determining whether or not a Latin square has a transversal is going to be very difficult. So perhaps the thing just to take away from this definition, aside from Latin squares and transversals, is just to say simply that some Latin squares of even order have no transversal. So next I'll take you through a little bit of history. So let me take you back to the early 18th century when the winter nights were very long and there wasn't very much to do. So here's a puzzle that might briefly keep you entertained. So if you take a ordinary deck of cards and just take out the picture cards, or the aces, kings, queens, and jacks, and the 4 different suits, like my picture here, can you put them in a 4x4 grid so that each row and each column has an ace, king, queen, jack, all of different suits? So from the nature of the talk, I can't, sort of pause and give you time to solve this yourself. But if you played around, you'd rather quickly find that there are some solutions. I think there are 2 non-isomorphic solutions. So here's one. And what relevance does this have to Latin squares? Well, you might be able to spot 2 Latin squares in here. So one of them, if I ignore the suits of the Latin square, then if I ignore the suits in the grid of the cards, then I get a Latin square in the values of the cards, like I have here. And then actually what happens is that if you go backwards, if you look at just the hearts, you'll see that that actually marks out a transversal. So each suit marks out a transversal, and this will give altogether a decomposition. So here's one transversal marked up by the hearts, another by the spades, the diamonds, and the clubs. So this is a Latin square that not only has one transversal, but actually I can find 4 disjoint ones at the same time. And this gives me a decomposition into 4 disjoint transversals, which pairwise share no cell. And while I'm here, let me tell you, so this has quite a long history, which I'll explain on the next slide, but it has an equivalent formulation. So I said there are 2 Latin squares in this picture. And the second one is if I now forget the values of the cards and instead look at the suits of the card. So down below, what I've done is exactly that. So on the right-hand side, I've forgotten here are the colors. And on the left-hand side, I've forgotten the letters. And these both form the Latin squares. And we call them mutually orthogonal Latin squares because they have this pattern where the symbols in one mark out a transversal in the other, and vice versa. And they're often called mutually orthogonal Latin squares, and this means that every suit and value pair appears exactly once. So for example, in the top left, there is a red A. And this is really inherent in the problem. I have each one the possibilities for cards at the start, and I've put them in the grid. So this is a pretty straightforward puzzle, but something that's a little more difficult is what became known as Euler's 36 officers problem. And it was supposedly a question around at the time, maybe even in the court of Catherine the Great. But Euler began sort of the rigorous study of Latin squares and wrote a long paper in 1782. And his officer's problem is exactly the same problem, but we take n equals 4 and we put it into n equals 6. So there are 6 regiments. If I have 6 regiments which have 6 officers with 6 different ranks, then can I put them in a 6x6 square so that each row and column contains an officer of each rank and of each regiment? So this one I can not spell answer for a moment for you by giving you a solution for n equals 5 here. So using chess pieces for their ranks and colors for the regiment. And this is a nice symmetric solution to it. And Euler considered this problem, and here's a screenshot from his paper. So he got close to a solution for n equals 6. So what he's doing above here in the 6x6 grid is see the 2 Latin squares, which are mutually orthogonal. He's writing one in Latin letters and one in Greek letters. And this is where the term Latin square comes from. But as you can see here, Euler is noting that these are not actually mutually orthogonal Latin squares, because the two of the possible pairs of Latin and Greek letters appear twice, D and epsilon, and B and zeta, I think that is. Okay, so this is as close as he could get to. And he asked the question in general, so we've seen the case for n equals 4 is possible, n equals 5 is possible. We don't know if n equals 6 is possible. Euler thought about this, and he gave examples that it is possible for all n is not congruent to 2 mod 4. And then conjectured more widely that if n is congruent to 2 mod 4, there's no Latin square of order n with a decomposition into transversals. And this you can check for yourself for n equals 2. There's exactly one Latin square of order 2 up to playing around with the symbols. And it has no transversal at all, so definitely true for n equals 2. And I would have thought it was true for n equals 6, because he couldn't find any solution, but he wasn't able to prove that it's definitely true, this conjecture. So I repeated the conjecture up there. So this took more than 100 years. In 1900 and 1901, Tarry showed that there are actually no examples for this problem, no solutions, which is maybe not the most interesting work. There's a lot of case checking, but there's some, I believe, cleverness behind it to cut down on the numbers. And then after this, I believe there were even some false proofs that the conjecture is true and that it was supposedly widely believed to be true. It is therefore maybe a bit surprising if you opened the New York Times in the 1950s, you'd have read that the major mathematical conjecture propounded 177 years ago is disproved, although it's not quite important enough to be above the fold. But this is because there was a disproof of this conjecture. So depending on your screen size and resolution, you might be able to see these three gentlemen here who are drawing a grid, which I think is a 10 by 10 grid. So what happened was that Bose, Parker, and Shrikanta constructed counterexamples for all n equals 2 mod 4. So it's false as soon as n is at least 10, and n is congruent to 2 mod 4. And here's a nice example, which is, so Bose and Shrikanta first disproved this for a couple of values of n, and then worked with Parker to show it was false for all n is at least 10. And this particular example, Parker found using a computer, and very early use of computers to disprove things. So I've highlighted here, here's one transversal, here's another one. I'll slowly bring them up. So there's maybe not too much of a discernible pattern here. And it does decompose into 10 disjoint transversals. So that's, I think, to bring us up to the end of the history. So I'll just briefly recap. So in that introduction, we saw that some Latin squares have no transversals. And what we've seen is that as long as n is not one of these two cases, there are some Latin squares of order n which not only have a transversal, but they decompose into transversals. So now from a more modern lens, perhaps, and to think about it in terms of with extremal combinatorics and then probabilistic combinatorics. So as I'm not quite sure the audience and how broad it is, I've put in a slide that just briefly says what I mean by this. So combinatorics is usually the study of discrete structures. In extremal combinatorics, we usually want to find the maximum possible for a parameter of some structure subject to some conditions. And then probabilistic combinatorics, usually I wish to study the properties of a typical structure, maybe by picking it randomly and seeing what that should look like. So for an example here, mostly I actually work with graphs rather than Latin squares. So a graph here is just some vertices with some edges between some pairs of vertices. Here are some vertices and here are some edges. And then what do I think about all the sets of vertices with 10 fixed edges, 10 fixed vertices, and 25 edges. So there's the constraint that I'm looking at. I'm looking at the graphs with 10 vertices and 25 edges. And then my parameter might be, say, the number of triangles they contain. So if I look at things from a point of view of extremal combinatorics, I'd ask perhaps what's the lowest number of triangles? Or maybe what's the highest number of triangles? And then from probabilistic combinatorics, I would perhaps pick one of these graphs at random and ask how many triangles it is likely to have. So let's do that for Latin squares and transversals and ask how far can it be for transversal, and also what should a random Latin square, what should its transversals look like? So indeed, how close to transversal can we get in any Latin square? And we know we can't get exactly close because of this example we've seen. We might be able to get pretty close. So let's define what we might mean by that. So here's a partial transversal, which is simply a transversal where I haven't said we should have the same number of cells as the order of the Latin squares. It's just a set of cells with different rows, columns, and symbols. And I've highlighted one. It's the possibly, I think this is, yes, this is the same example as of a Latin square. It doesn't have a transversal. It's the Latin square for Z6. But it does have a partial transversal of order 5. So we got pretty close to a transversal. And the Reiser-Brownlee sign condition in 1967 says essentially that's as bad as it should get. So it says every Latin square of order n should have a partial transversal with n-1 cells. And it actually perhaps should have a full transversal if n is odd. And like many conjectures that are pretty tricky, we can approach them in different ways, but the main way this has been approached has been trying to show increasingly lower bounds for how large a transversal, a partial transversal, I should be able to find in any Latin square. And in this case, it's actually not too difficult to find a partial transversal which is most of the cell, contains almost n things, let's say. So usually in combinatorics, I call this as an asymptotic result if it has n minus little o n cells in it. And this was already achieved by Brewer, De Vries, and Feringa, and independently by Wilbright in 1978. He showed that in any Latin square of order n, you have a partial transversal with at least n minus the square root of n cells. And then not long after this, this was improved to a nice polylogarithmic point on the number of missing cells. So this was by Shore in 1982. The slight wrinkle that there was an error in his proof that was only noticed and corrected later. They were essentially using the same methods, I'm told. But this was by Hatami and Shore in 2008. And they showed that every Latin square of order n has a partial transversal that is only missing something of the order of log squared n cells compared to a full transversal. So this was a point that stood for the best part of 40 years. And then pretty recently, there's one of Kifach, Prokowski, Sidikov, and Yefremian, who are all combinatorialists, who showed that every Latin square of order n has a partial transversal. They got this number of missing cells down from something of the order of log squared n to order of log n over log n cells. And it's a really nice point. There's something very fundamental in our methods for approaching this that kind of comes up against a very strong barrier, log n over log n. And it's really very impressive that they got to it. And then a few years after that, I showed that every square of order n, as long as n is large enough for the methods I was using to kick in and work, they will have a partial transversal with at least n-1 cells. And these last two results are in part indicated by my title. So both of these results were really shown as graph theory results. So by thinking about Latin squares, not as Latin squares, but as graphs. And this allowed us to apply both techniques, but also perspectives from graph theory to make progress. So the next thing that I'm going to do, I think, unless I've misremembered Slides, yes, excellent, is to show you how you can think about these Latin squares as graphs, in particular graphs whose edges have colors. So we're going to be considering them as properly colored graphs, and a proper coloring is where we've colored the edges of the graph so that no two edges of the same color share a vertex. Here's a very simple graph with two edges. On the left is a valid proper coloring. On the right, it isn't, because there are two red edges that share a vertex. And then we're going to be thinking about complete bipartite graphs, which is bipartite means I can split the vertices in two so that all the edges go across, and complete means all possible edges are present. So we'll call this graph K33, for example, I've drawn on the right. Here. Right. So the Latin squares of order n are equivalent to complete bipartite graphs, K and n vertices in each class, which are properly colored with n colors. So for a Latin square, for example, of order 6 here, if you create a new vertex for each row on the left, and a new vertex for each column on the right, then for each pair, row and column, I'll create an edge, and I'll look within the Latin square, and I'll give it the color corresponding to that symbol. So here, the 6 entries that have symbol 1, I've assigned red, and I'll put a red edge for each of those entries over there. And I do with each of the symbols. 2 can be blue, some green for 3, orange, some pink, and some other drab gray color. So already perhaps an observation that's a little ironic. So on the left, visually is a very clear representation of what's going on. And on the right is a bit of a mess, and it's very hard to see actually which edges are which color. But if you do graph theory a lot, then it really is much easier to think about what's going on the right there. Okay. So this is an equivalent, so you can also go backwards and create a Latin square from such a graph. And the Latin square properties exactly give you this proper coloring. So we have the rule that each row can only contain the color red once, and therefore this corresponds to each vertex representing a row can only have one edge, which is red next to it. So these are my Latin squares, and I want to consider within them a transversal. So transversal corresponds to some disjoint edges that all have different colors. So we call it a perfect rainbow matching. I should have an example here. The transversal on the left-hand side here. And then on the right, we have 6 edges that share no vertices, which corresponds to them as cells sharing no row and sharing no column. And they also have 6 different colors. So we say this is rainbow. So we can, instead of thinking about Latin squares, think about complete bipartite graphs and properly colored with colors, and look for perfect rainbow matchings instead. And under this formulation, the Reiser-Brothers-Stein conjecture is saying that any properly colored graph K and n that's using n colors has a rainbow matching with n-1 edges. So almost as perfect rainbow matching, just missing one edge, and also n edges if n is odd. The proof that was on the result is in the previous slide, which shows for large n, there's always a rainbow matching in this setting with at least n-1 edges, is a little bit long, but I'll try and just say something incredibly broad about these sort of results in general. So, what I was doing there. Okay, so in general, you might have some conjecture in combinatorics that you'd like to prove. And here's here's an abstract representation of what you might wish to do. So you're trying to find within any complete bipartite, properly colored graph with n vertices on each side using n colors, or equivalently in a Latin square, and find as large a partial transversal as possible. And sort of a first step often to showing these sort of things is to at least find some approximate solution, as I mentioned before. So here you're looking for a partial transversal with close to n cells, and we're just trying to get that as close to n as possible. So exactly that's the result we're looking for. And sometimes on its own, this is a really difficult problem. I think in this case, it's not too bad at all. And nowadays you can do it by fairly standard methods as well. Okay, so the sort of one of the points I mentioned was by Shore, corrected by Hatami and Shore, and roughly what they're doing is taking any approximate solution and then trying to make some alterations to make it look better and better. So it might look like this. And then compared to that, the sort of where the graph theory techniques might come in is in this follow-up one by Kiefer-Spolsky, Pseudocraft, and Yepemian. What they did was they took an approximate solution which looks rather random, and this is using something called the semi-random method, which is some big method in combinatorics. And very roughly, the issue with this is if you just try to pick out sort of edges randomly, you'll sort of see that this goes wrong quite quickly. So you could greedily pick out an edge of some color or a cell of some color and delete the rows and columns that you have left behind. And then you'll also have some symbols that you don't want to use again, or some colors. You'd also have to delete edges of those color. And if you do this repeatedly, can you analyze this and see if you end up with a nice random looking solution? And this part looking sort of random might help you to be able to modify it and therefore be able to extend it a little bit further to get an even better drawing than before. And then what I was doing is a related to a method called absorption, which is to take a very carefully constructed approximate solution and then at the end be able to modify it in a sort of one big step to get very close to transversal. And this is sort of a principle that's sort of known by absorption, sort of, I can say, codified by Rodel, Rutchinsky, and Samarady in the 2000s. And it's a little bit almost vague, so that means it's useful in lots of different ways. You can implement it in different ways. But essentially, it's saying that at the start, when you're trying to find bits of a partial transversal, this is very easy to do. So you shouldn't be too lazy at the start and just do it in any sort of way. You should plan for the future and try to come up with something that will help you out later on whenever it becomes difficult, because you've used most of the rows and most of the symbols. Okay. So I will say nothing more about that proof and move on from the extremal side of things. And just note that, so here, what do we note? We noted that you can get very close to a transversal, at least if the Latin square is large. So if the order of the Latin square is sufficiently large, then you can find a transversal that's missing only one cell. So what about probabilistic combinatorics then in its perspective? So we've been sort of trying to hunt down the strange behavior, these Latin squares, which don't have a transversal. And we have quite a few examples. There are more examples, we call them extremal examples, that don't have a transversal. And they don't all come as kiddie tables. They can be constructed from them in some way and modified a little to give you lots of examples. But still, we want to know, is that sort of a typical thing? Are those examples a large proportion of Latin squares or not? So we know these two extremes are possible, and where might a random Latin square sit? So to make things a bit more concrete, let's pick is the random Latin square, so uniformly at random. So let's take a set of Latin squares of order n, which all use the same arbitrary set of symbols. So the numbers went up to n. So we have a nice finite number of them. And then let's just pick ln from this set uniformly at random. So here I've done the case for when n equals 3, but really I'm thinking about n being much larger. And then the sort of concrete question we want to ask is, does a random Latin square ln have even a decomposition into transversals with high probability? So with high probability in combinatorics we use this just mean, does the probability that a Latin square decompose, does it tend to 1 as n tends to infinity? And you can also think about this as saying to what extent is Euler's conjecture false. So when n is equal to 2 mod 4 and n is at least 10, we know there are some counterexamples to his conjecture. That is, there are some Latin squares of order n which decompose in transversals. But what sort of proportion are these counterexamples that some people call Euler spoilers? It's a bit of a mouthful, especially in my accent. So this is our question here. So I've already sort of jumped and indicated through this question that we should expect a random Latin square to have lots of transversals and lots of disjoint transversals. So here's the question again. Here, this is the previous example I had just as an illustration. So it turns out to be quite hard to even show that there's one transversal with high probability. But we do now know that due to Kwan in 2016. And the methods he used can be extended a little bit, as was done by Morris the following year, to show that you always get a small linear number of disjoint transversals with high probability. So he found a few more. And then Kwan and Ferber find, again, an approximate answer to this question. So they showed that you can get close to having n disjoint transversals with high probability. Just a side note for accuracy's sake is, oh, I've taken out the, so they showed this in the very closely associated setting of Steiner triple systems, but their methods would and should we expect them to translate through to prove this. But earlier this year, I finished with Candida Boutel, who was for a while my postdoc and is now in Birmingham, who showed the answer to this question is yes. So as well as saying with high probability, sometimes we'd say almost every Latin square has a decomposition to transversals. So this again uses a lot of different graph theory techniques, as I've commented on briefly on the next slide. That's our result there. So the first thing I say something about the random model. So it's frustrating as a developer. It's sort of unexpected almost how difficult it is to show that there's one transversal with high probability in a random Latin square. All the examples we have which don't have a transversal, they all have some algebraic structure or are very close to having an algebraic structure. And therefore, in a random Latin square, somehow we shouldn't expect this. We should expect to be able to find a transversal. But it turns out it's a hard model to study. How do you pick a Latin square uniformly at random and sort of decide what properties it might have? Kind of heuristically, one reason it's hard to study is that it's quite difficult to take a Latin square and make some small change to it and swap around a few symbols and get another Latin square. This makes it quite a rigid object. And this makes it hard to study, but due to Kwan, he was able to do this. So he used something called the triangle removal process and some real breakthrough results by Kivash. About just over 10 years ago now, he showed that designs, this far more general thing than Latin square, they exist in general. So then I've just noted some words here, which to give you maybe just some idea of the range of techniques that we're able to use from graph theory and how important this is that we have these techniques and this perspective from there. So I've mentioned absorption, which I mentioned before, the semi-random method that I mentioned before, we're using a different way to approach random Latin squares due to Goldson and McKay and Wanless and McKay from sort of the 90s, which are switching methods, and also using something called the deletion method. And especially if you're maybe starting out in your careers of writing papers and things, I thought I should maybe note that a lot of this is a question of whether we can prove the result as well. But it's a sort of result where you also need to bear in mind whether you can actually write down a proof of this, because it can get pretty long. So it really needed several key innovations to prevent the overall complexity of the paper spiraling. It's still the longest paper I've been involved in, at some 93 pages or so. But really, there's some key ideas in there that just sort of keep a lid on this and keep it from getting just terrible. And let me just maybe pick out another point, which is, so I mentioned this is sort of another perspective of this whenever n is equal to 2 mod 4, n is large. This gives you a disproof of Euler's conjecture. By saying that as n gets large, the proportion of counterexamples grows to 1. So in particular, at some point, it's definitely non-zero. And if it's strictly bigger than 0, then we must know there is some counterexample out there in the world. And so this gives us a non-constructive disproof of the conjecture. We can guess some things about what they might look like, counterexamples, because they should look like a typical random Latin square on average. But this is known as the probabilistic method, and it's a really simple idea, but it's one that is astonishingly useful and somehow harder than you think to come up with. So in the 50s in particular, but maybe from the end of the 40s, Erdős, sort of great pioneer of combinatorics in general, really showed us all how to use probabilistic method, and it's key enough that there's a famous and excellent book called The Probabilistic Method by Allen and Spencer. And using this, Erdős is able to prove all sorts of things that we don't have these constructive examples for. So, for example, if you've ever come across Ramsey numbers, the lower bound for Ramsey numbers are still best via the probabilistic method. And we have no constructive way. We can't write down what a graph is that has these conditions. We can only say that using some appropriate random distribution on graphs, if you pick it randomly, then there will be some graph with these nice properties that we want. Okay, well, let me just wrap up there with a final summary. So I talked about Latin squares and indeed transversals in them. We know now that some Latin squares have no transversals, but every Latin square is, when n is at least large, and perhaps in general, is really very close to having a full transversal. Whenever n is not equal to 2, 6, some Latin squares decompose in transversals, and in fact, this is true of a typical Latin square. If you pick one at random, it's likely to have such a decomposition. Okay, so I'll finish there. Thank you very much for your attention.